Just one other thought. I mentioned about Bacon and something else. If you read the article that I've written, which Philip will make available, the article's called Goethe and Modern Science. So it's actually about a great deal about modern science and a bit about Goethe at the end. And it goes right back to the medieval period, which is actually when modern science began. What actually happened in the 17th century, it's not Renaissance either, it's 17th century, was that, as Crombie put it, science was transposed into the key of mathematics. That is that mathematics was already part of everything, but mathematics was then made the dominant thing. So that was the shift that took place. And what the history of science shows is that the development of modern science was highly influenced by mathematics. And Bacon took a different view. There was another side to it when people began to do very empirical observations, making new discoveries. The point about the mathematical approach is it didn't make any new discoveries. It was actually, the mathematicians were always concerned with phenomena which were already known and showing how they could be understood or understood differently. And they often said, well, we don't need new phenomena, we've got enough. Because they also saw this mathematical approach as leading them back into the thinking of God, because mathematics and religion and science were completely interwoven at that time. Now, one book which is highly accessible, where you can read about this, is Margaret Wertheim's book, Pythagoras' Trousers, God, Physics and the Gender Wars. And I highly recommend that book. She did her homework. When she set out to do what she did, she got a double shock. She had not grasped at all, she said, how it was the influence of mathematics was the dominant influence in the development of modern physics from that time onwards. Nor had she grasped at all the way it was tied in with religion. And this is a highly readable book, very enjoyable, but also everything she does in it is well researched and not done in a silly way at all. So I recommend that. There may be copies in the library downstairs. Yeah. I strongly recommend that. It's necessary background. So, you see, if one knows about that, you will understand a lot of things which otherwise you won't quite get. But I just mentioned, you see, if you know that background, it is surprising that Bacon underestimated mathematics. In fact, he was somewhat opposed to mathematics. He said that mathematics is useful as an exercise for the mind, like tennis is useful as an exercise for the body. Because tennis had just come in at that time, it was the big thing in the Royal Court. It's a new thing. Now, this underestimation of mathematics, for example, he did not at all like the way Galileo worked, with the work on the accelerating bodies and falling bodies and so on and that. He saw that what Galileo did was simply wrong. Galileo discovered that for bodies with uniform acceleration, the distance gone from the start, say, is directly proportional to the square of the time. So in twice the time you go 4 times the distance. In 3 times the time you go 9 times the distance. This was considered to be an utterly miraculous discovery. Clear evidence that they had penetrated to God's thinking in the universe. Now, Bacon wouldn't hear of it. He said when it's applied to falling bodies, it's nonsense, he said, because the bodies don't fall like that, which is true. He said you've got to study all the different cases. So this is where Bacon loses it. You've got to study all the different cases. Well, if that's the case, you miss the whole thing. Because the genius of Galileo was to say, let us suppose this is falling in a vacuum. Which, of course, was more than genius, it was audacious. Because at that time, people said there cannot be a vacuum, because Aristotle said there cannot be a vacuum. So he's compounding his felony here very, very much. And eventually, of course, it turns out to be what we believe to be true. But Bacon would have had people investigating all sorts of different bodies falling, all the different cases. And, of course, you would never have discovered anything. Now, Goethe hugely admired Galileo, and he commented on Galileo that he knew how to do things. He said he knew how to find an instant's worth 1,000. And he also said this thing he understood so well. He said he knew how to solve the problem by turning the problem into the solution. And if you study how Galileo changed the whole science of motion, even so he changed almost common sense into uncommon sense and made it look like common sense. He actually, the problem, if you drop a ball from the top of a tower, if the earth is at rest, it should fall straight to the bottom. If the earth is moving, it should fall far to the west. Yeah. The earth's turning one way, it should fall. Clearly it doesn't. Complete empirical evidential proof that the earth is at rest. Not so, says Galileo. Now he changes it. He said what actually happens is that body that's falling keeps up with the motion of the earth even while it's falling. So it ends up with the result that a body falls on a moving earth in exactly the same way that the body would fall if the earth wasn't moving. And Goethe says, brilliant, that's how to do it. You turn the problem into the postulate. So he postulates that keeping up with the earth is the natural thing for the body to do. This is now the idea of inertial motion coming in. And Bacon couldn't understand this at all. Goethe saw right through to what Galileo had done. Brilliant. He was a great hero of Goethe's, but don't tell that to the Goethenists, because they don't like Galileo for another reason. Anyway, there you go. Because another reason why, you see, context, then you begin to understand. Another reason why Bacon was against mathematics, this was the primary reason, and made a big fuss about how it wasn't very important, is because of his position at the court. First of all with Queen Elizabeth, and then with King James I and VI. Now, I don't think King James liked him, for various reasons. And Bacon's position was tricky. Now, in those times, you could fall from grace like that. You could be the number one favourite, and half an hour later, you're in the Tower of London waiting execution. And it really was a very dangerous time to be alive. We know about this, you read about the Elizabethan poets, because this is the time also looking all the time for Spanish spies. Spain was the big fear. Later the French were the big fear. Napoleonic spies, Spanish spies, whatever it was. Then German spies, all spies. Russian spies, there's always been spies. These are Spanish spies. You got killed. If someone thought that you'd been colluding with someone who had Spanish connections, you were dead. It didn't matter who you were. And these are people who are quite high up. So you've got to watch your back, your front, your side and everything these days. And one reason why he may have been so opposed to mathematics is, of course, because the change that took place with Dr. John Dee, the famous John Dee, the magician, Kabbalist, whatever, a mathematician. And this older idea of mathematics as being symbolic of the universe. And you could conjure spirits through mathematics. You could conjure angels through mathematics. This is what these people maintained that they were practicing. This is the occult tradition, the Hermetic tradition, the Kabbalah added in at this particular time, which brings in so many influences, and this was a real big thing. And mathematics there is central. Now it's operational. It's magical operational you can actually influence the world by operating magically with number if you understand it. And that's what mathematics meant to a lot of people. What it means to us was only just beginning to come in. And so when Bacon was opposed to mathematics, what he was actually saying is, look, I'm not having anything to do with that. Because King James I and VI didn't like that kind of thing. And so he had to be pretty careful. So you see, if you find out about, well, why did that person say that? And so on that, then you begin to understand. So then he goes down in history as if there was some profound philosophical reason. No, he's probably saving his neck, literally, you know? So all this background gets us nowhere. The other thing I would mention is this instance worth 1,000 of Goethe's. Where did he get it from? I mean, it's all very grand what we've done, but did he come to it that way? Well, I think it's there in the literature. He actually, after his work, you see, it's not in the 1792 work, this is not mentioned at all. No mention of anything like this. It comes in the 1810 work. So he'd had 20 years in between. And he was very oppressed by the way he was treated, by the way his work was ignored, by the way people said Newton's got all the answers, shut up, Goethe, go off and write some poetry and so on and that. That he actually spent years and years and years researching the whole history of colour. Now, if you go to the Renaissance, you find there people do talk about this. I've not found anything about the red, but Leonardo da Vinci does indeed talk about the blue. And I've got two quotes here, but God, I can only read one of them. But this business about experience shows us that the air must have darkness behind it, and yet it appears blue. If you produce a small quantity of smoke from dry wood, and the rays of the sun fall on this smoke, and if you place behind the smoke a piece of black velvet, on which the sun does not shine, you will see that all the smoke which is between the eye and the black stuff will appear of a beautiful blue colour. This I mention in order to show that the blueness of the atmosphere is caused by the darkness beyond it. This is Leonardo da Vinci. And then there's another long quote which I won't go into. Similar. Actually, yeah, and he actually says, if you go to the top of a high mountain, I'll read it. Thus the sky looks blue by reason of the darkness beyond it. And if you look towards the horizon of the sky, you will see the atmosphere is not blue, and this is caused by the density. And thus, at each degree, as you raise your eyes above the horizon up to the sky over your head, you will see the atmosphere looking darker, that's bluer. And this is because a smaller density of air lies between your eye and the outer darkness. And if you go to the top of a high mountain, the sky will look proportionately darker above you as the atmosphere becomes rarer between you and the outer darkness. And this will be more visible at each degree of increasing height, till at last we should find darkness. Leonardo da Vinci's Notebooks, Volume 1. That cannot possibly have missed, Goethe can't have missed that one. And I haven't found anything anywhere, I've not looked, found this by accident. Everything comes by accident to him who doesn't know what he's doing. The thing is, never by accident come across anything about the red, but there's bound to be something somewhere. I only need someone to go and look. One of you could go and look. If you find anything, let me know, and then I'll make another piece of paper about the red. But with knowing what Goethe did, and reading that, it does seem to me very likely that this Bible phenomenon he discovered in books. Of course, it's one thing to discover something in books, the thing is to discover it. That is to see its significance and to be able to use it. So I'm not in any way denigrating Goethe for that, because I have the problem, always. I don't now, because what I've just done now I don't do now. I know that's an oxymoron, but never mind. The thing is, when you're doing this with people, there comes a point where you jump to the primal phenomenon. So you fudge it. Because someone might ask, well, where did Goethe get this from? And then it becomes a bit of a problem. You say, well, you see, he looked into the phenomenon. But it's not convincing. I noticed this as I did this over the years, I began to feel there was a kind of gap. And I thought, well, he brings this up 20 years later, and it's just there. Where did he come to this? Through observation. And I think he got it this way. But that doesn't mean I disrespect Goethe for that. This is the case. Copernicus, with the sun in the centre, where did he get it? Well, he found it in a book. He found it in books by ancient Greeks, where they'd had all this idea, another lot of the ancient Greeks. And he took it from there and worked with that, and so on and that. Because it's... what's the name of the man who's now referred to as the Copernicus of antiquity?
Aristarchus.
Thank you. They should, of course, refer to Copernicus as the Aristarchus of modernity. And that's where he found it. And he says so in his book, De Orbium Caelestium, 1453? 1553. He actually says in a prefatory letter to the Pope, this is where he found it. Of course, people don't forget that, don't even know it. And then they invent a story about how Copernicus came to what he did, which is the biggest load of baloney you've ever come across. This is another thing I used to teach in detail, to show people how you only understand when you go into the context, the background. And how it happens was entirely different and all to do with Neoplatonism and heavens knows what. So Copernicus found the Copernican system in a book. But what he did with it, it's like that advert. What is it? It's that advert. There's an advert where the bloke, there's a girl doing all this stuff. And there's this bloke with his stubble. And he turns and said, yeah, it's what you do with it that counts. Well, that's it. It's like that. It's like that. It's what you do with it that counts. You know. Okay. So, what I'd like to look at now is Newton. Now, Newton's work comes in two parts. First of all, a letter, which is really a research paper, to the Royal Society in 1672, entitled The Origin of Colours. And then his magnum opus on light, optics, usually spelled O-P-I-T-C-K-S, 1604. That's a big book. The 1672 one is quite a small piece of work, presented to the Royal Society, but it should be said that Newton was involved with optics throughout his life, and he had been lecturing on optics in the University of Cambridge in the later part of the 1660s and early 1670s. I don't know whether his lectures have actually been published, but they contain a great deal of material. The famous paper is the 1672 one, in which he purported to show, directly by experiment, that the origin of colours, as he put it, was what he called differential refrangibility. That is, that when light is passed through a prism, different colours are refracted different amounts, different angles. And that you get this spread of a spectrum on the other side. And he maintains that those colours are in some way, and this gets complicated, already there in the light coming in. Which is usually called white light in physics. But clearly it's not white light, it's completely invisible. Because it needs to be said that light is invisible. Everyone thinks of light as being visible, but of course it isn't. I used to demonstrate this years ago. I had a black box made, painted outside and inside totally black, and a sheet of glass in the front. And the idea was, you had a small entrance hole at one end and a small exit hole at the other, and you put tubes there, tube and tube, and you put a light against the tube there. In a totally dark room, you would have a screen on the other side, and you would see a circle of light. And you would say to the students, and what do you see in the middle? And they would say nothing. There's nothing there. And I had this box made, and instructions, used it once a year, to the technician not to dust it, which he found very hard to do. And my colleagues said, who were very clever people, well, you simply won't see anything. Exactly, I said. Because a 14-year-old boy sees it rather differently, because he expects to see something. He expects to see light. And what you discover through this is that light is invisible. Now, we don't think of it that way. We think of light, say, streaming across space from the sun, or rays of visibility coming across. Light, luminous light coming across. Well, why is space dark then? If it's filled with light, why is space dark? The answer is because light is invisible. It only becomes visible when it illuminates something. It is when light encounters matter, it illuminates matter and thereby reveals itself. So literally, light exists in that sense by reflection. The ancient peoples did distinguish these two different kinds of light. Ancient philosophers did. Modern philosophers don't and get totally muddled up about this. So light is invisible. So it's very awkward when you draw diagrams with nice straight lines showing the light, or you talk about white light. You're implying that there's something visible there, and there isn't. So we need to just hold that in the back of our minds, because it's all a question of seeing the idea, you see. You see, my colleague said you won't see anything. That's all. That's the empirical fact. You won't see anything. But you can see something. You can see the idea. My God, light is invisible. That's different from, oh, you won't see anything. That's the empirical fact. The phenomenological fact is seeing the idea. And that's the difference between empiricism and phenomenology. You see, light is invisible. That is what I see. I see light is invisible. And you do see it. It's there. It appears. It's astonishing. We're going back to what we're talking about appearing. It appears, like Duchenne. It appears light is invisible. Sounds daft, but you can see this is what happens. The idea appears. But not to my colleagues. My colleagues were very clever. Simply knew that you wouldn't see anything. So they missed the idea. It's fascinating. These guys were clever. They thought I was not terribly bright. They were quite right too, but I mean, anyway, there we are. So, when we talk about white light, it's not really like that at all. So we have to just mention that. Anyway, what he did is he shone this light through, so you got the colours. And then he says, and of course this is very peculiar, that the colours are there in the light already. And he can demonstrate this experimentally, he says. The colours are there in the light already, and the prism separates them, because each colour is refracted by a different amount through the prism. It's called differential refraction. And then he does, this is very different from Goethe. Goethe says, the colours are excited in the light when the conditions are right. When the conditions go, the colours go. There aren't any colours there. Newton says, the colours are there all the time. And they're developed out of the light when you refract it. But they're in the light all the time. You see, it's completely different. Now, I have to say, he then says that he has an experiment. There's lots of experiments. I have read his original work, this original paper. I have a copy. I found it in a book published in 1934. It's never mentioned in books now. One needs to go back to older books. And there are extracts from it in my book in the later chapter. He had an experiment, right? I'll come to that in a minute, which he called the experimentum crucis. Mistranslation, we don't know, from Bacon. Experimentum crucis, which has been taken as being the crucial experiment, the crossing experiment, that when you've crossed that, you can't go back again, as it were. It's the crossroads. and that tells you what it is. And this experimentum crucis will show you that in the prism there are colours which are refracted differently, and that's where you get it from. And he can demonstrate this, he says. Well, I'm going to mention that in a moment, but I should say that at the time nobody believed him, and his time was taken up for a decade almost with objections to his work from various members of the Royal Society. And I've gone through the letters, and I have 10 or 11 objections from different people objecting to this and saying, no, Newton, you haven't done that at all. And he didn't like that, and it caused him a lot of acrimony and a lot of bother, and he said he wouldn't publish any more work on this at all until certain persons were dead. And the certain person was actually Hooke. And he hated Hooke and don't think Hooke was too keen on Newton. Hooke died, early on in the 1700s, and so then Newton comes out with this big book because he can publish it now because Hooke's dead. And that was it. And he wasn't going to let Hooke know what was in his book. And this is it. But what he did in this experimentum crucis... first of all, let's look at what he did first of all in the first part. He tells us what he did. He went and he procured himself a glass prism to try the celebrated phenomenon of colours. This is in his notebooks. He went to a fair, and you could buy these prisms at fairs. And he went to a fair and bought it, or else he sent a servant to buy it. And he then pulled down the window shutter and made a tiny hole in the window shutter. And he then put the prism in the way of the light which was coming through. And on the wall opposite or on the screen, he got a full spectrum of colours covering it. If that light's in the way, you need to move. It is very beautiful, but you also need to focus on what I'm saying. Because if you do, you will actually understand that and why, particularly the one above, why it's elongated and why it seems to be curved a bit at the end. You will understand something about that. Now, the interesting thing was that on that wall or on that screen, you get the full, what is called the full spectrum. Red, orange, yellow, green, light blue, dark blue, whatever you want to call it, blue, indigo, violet. I'm not going to bother about the names and whether there's indigo or there isn't. I couldn't care less. You've seen the phenomenon. You get the whole lot there, which we saw with the narrow strip. And as he said, that those are the colours are already there in the light, and the prism develops them out of the light. Now, his further experiment, many experiments, what he noticed was, he's made a small hole, but he notices that the image on the screen is not a small hole, it's elongated, and it's 5 times longer than he expects it to be. And he's very puzzled by this. And he does many different experiments and measurements to eliminate, could it be due to that? Could it be due to this? Could it be due to that? Etc. And he eliminates everything until he comes to the conclusion that it is because those colours are there in the light and they're spread out. Now, in a minute, we're going to look at this for ourselves, because we can now approach this in a Goethean way. But since I've talked about this, I better just do the next bit. His experimentum crucis was to take a second prism behind the first. So he's got the first prism and the light coming through it. Now, instead of forming the spectrum, he puts in the way a second prism, and he arranges a shutter, so that he can actually select light from the first prism of one colour only. Let us say red. All the rest is blocked. And he can then send that red through a second prism onto another screen. You'll only get red. You get no more spectrum, you get red. Then you can do it with the other colours. Well, let's go straight to blue. he can do it with the blue. He can block the red and everything else and just let the blue through the second prism. And that will be refracted onto the screen. And that's where he shows that the blue is definitely refracted through a bigger angle than the red. And all the colours are refracted through different angles. That's differential refraction. And that's his key thing. And that everyone in the Royal Society agreed that he had made a discovery there. Then they said, that's your discovery. And he said, yes, but actually what that means is, with the first prism, it's doing that. But all the colours are there in the light, and somehow or other, when they're all jumbled up together, they disappear and make white light, or whatever you want to call it. And then when it goes to the prism, because of differential refraction, then they're separated out. The colours are there already. Now, I won't go too far into the logic of this, but what he does is a very clever inversion there, which I'll leave you to think out for yourself. And they said, no, that's not true, Newton. There's no evidence for that. Now I'm going to look with you at something now which will show you what's happening in this experiment. One thing more. What is it? Oh, come on, it was there a moment ago. Yes. Why does he start off like he does? I remember reading a book by this chap in California in the 1960s who got very famous with a book called The Making of the Counterculture, and then another book. What's his name? He was so famous, of course, everyone's forgotten him now. The Making of the Counterculture. And then he wrote another book, and he had this, what he called the need for rhapsodic physics. Physics should become rhapsodic. And this is what Goethe had done. And in this book he goes on, and what a terrible thing it was that Newton did. Instead of investigating light in all its wondrousness in the natural world, he forced the light through a tiny hole and looked at that. What a terrible man Newton must have been. And on and on and on and on. And of course all the hippies thought it was wonderful in San Francisco, smoking pot, and yeah, great, that's wonderful. And it got repeated and repeated and repeated. So what was Newton doing? Being a wicked man, constricting the light through a tiny hole? No. What was his motivation? Newton was concerned with images formed in telescopes. This was new. Galileo and others had made refracting telescopes with lenses. Now, one of the problems with these telescopes is that they didn't give good images. Various distortions, but one distortion is called chromatic aberration. What that means is you get colour that you don't want. Your images are coloured, and you know that colour's not there in the phenomenon. It's actually been produced as an artifact by the telescope. Hence it's an aberration. You have got unwanted colour. And the question is, can we get rid of unwanted colour? And Newton was experimenting on colour to try to see if he could make a discovery which would enable them to get rid of unwanted colour in telescopes. So Newton wasn't investigating colour to come to a deep understanding of colour. He was investigating colour to get rid of it where it wasn't wanted, which you're all very grateful for, because those of you who have cameras and so on and that, if your pictures came up with all those little colours on, which aren't there, you wouldn't like it at all. So I always say to people who don't like Newton, don't forget when you go to bed tonight, say, thank you, Mr. Newton, for sorting this out, so my camera works nicely. Anyway, that's what he was doing. Now, what is that tiny hole in the window shutter in a darkened room? It's an image of a star. He's made an artificial star. The light coming in is light from the star. What is a prism? A prism is half a lens. There's a prism. There's another prism. There's a lens. Okay? A prism, you can make a lens out of two prisms back to back. Well, you don't need both halves, actually, you only need one. So his prism is actually a model of a lens. The hole in the window, in the shutter, is a model of a star. He's making a model of the light coming from a star going through a lens. It all makes sense. It's not he's a wicked man, squeezing the wonders of light down through a tiny hole. What a terrible mind he must have, and so on and that. It is, he knows what he's doing, that's what it is. So now what I want to turn to is this elongated image that he comes to, because it says on the screen, it's elongated. And that, he says, is because of differential refraction. Here we go. So we're going to now do this in the Goethean way. And Philip's going to hand out the prism, see?
I think everybody's got it.
Everyone's got a prism. So what I want you to do, you start with that one, where you see both together. That one and that one. Okay? Oh, I'm giving you my prism.
Or do you want to highlight it? You like from? Okay, you from? Is this your 9? Oh, that is yours.
You can incidentally do this by taking a sheet of paper and all you need to do is to make a pinhole in it and just put it up against the light and do it. That's Newton. And then you can also take the same piece of paper and just put a pencil dot on it and you can do the same thing. You don't need this, but health and safety does not allow me to use pins with you. Okay. Well, there, I want to look at the white circle. If you take the big white circle, what you see is you've got the colours at the top and the bottom. And you see the amount of spread depends on the curvature. If you look at the top of the circle, you notice how it's become elongated through the prism. Mm-hmm. If you look at the top of the circle, you've got the maximum spread, the same at the bottom. If we look at the extreme sides of the circle, halfway down, there's no spread. And the amount of spread in between varies. Now, if you had done that, we could have done that. I'm not going to pass these around. We could do that with this. All you need to do is to start rotating it. And then you see the amount you get depends on the angle until it's vertical and you get none. Well, some of you saw that yesterday anyway. Well, that's what you've got here. Because of the shape, you get maximum spread of colour at the top and bottom, 0 at the sides, and different amounts in between. Now, if you make it smaller, what actually happens is those two boundaries then come together, and you get green. But because of the way the colours have spread, when they combine, what you see looks oval or elongated.
Yeah.
Because of the way the colours have spread. You can see that in the first place. Mm-hmm. And there you've got Newton's elongated image. Of course, we're doing it this way. He does it out there with light, whole light prism screen. We're doing it here just direct looking. But that is what Newton saw. And we can see ourselves, from all that we have learnt, that the origin of what we're looking at now has got nothing to do with all the colours being there in the light and then being spread out by the prism, it makes perfectly good sense in terms of the coming into being of colours through the lightening of dark and the darkening of light, and when those two meet. So here we've got a case, these colours are excited in the light because the conditions are right for that. They're not in the light and then developed out of the light by the prism separating them, as Newton says. So this shows us, and when I say this, you've got to remember, everyone in the Royal Society thought that Newton hadn't shown that. They thought he'd shown differential refraction for single colours, but his explanation that the formation of the spectrum at the first prism was due to differential refraction of colours that were already there in the light, they thought was wrong. Now this, of course, is the thing that you grew up with, and that Newton was right, and everybody thinks Newton is right. And that's what's taught in schools, and this is what Goethe thought Newton meant, and Goethe thought, that's why Goethe thought when he looked through there, on the white wall there should be colours everywhere. Later on he realised it wasn't quite like this. So what Goethe said about this is that this is a complex phenomenon. This is a secondary phenomenon. This is a complex phenomenon. It's got different parts to it. The lightening of dark, the darkening of light, and the mingling of those two. And he said Newton has taken a secondary, complicated phenomenon for a simple phenomenon. Newton took this as the simple phenomenon, passing light through a hole. This is actually a complex phenomenon. And then what's he do? Well, he does the Rumi trick. He tries to get to the milk by way of the cheese. He starts with this, which is the cheese, and he shoves it back into the light and says all those colours are there in the light already. That's finished product thinking. Now, Goethe's thinking follows through the coming into being of the colours, the arising of the colours in light. You can see how each of these colours comes into being, why it is where it is, why the order is what it is, and so on. And so that's the difference between them, and it's extraordinary. This is the dynamic approach. All I've been talking about, the dynamic approach, is now actually being done. We've done it here with colour, where actually it's very easy to do it. It's much easier to do it than in the phenomenology, but then, of course, with the phenomenology, you learn something else. And Goethe's way of working is phenomenological, because he sees the idea in the phenomenon. I'll come back to that a little bit later. And of course, what I've done there is I've done the reverse case, which Newton doesn't describe, because you don't have a dark hole in the middle of light. You see, so you never investigate that one. And there you see the opposite, where it's the same phenomenon, but now you have the purple magenta in the middle. Incidentally, I should mention that physicists have now constructed an apparatus that will allow you simultaneously to show the opposite spectrum, the counter spectrum as it's called, from the dark surrounded by light instead of the light surrounded by dark. This has been done in Germany. And I was going last year, exactly this time last year, to a conference where this was on, but unfortunately my breathing was so bad I couldn't actually go. I had to cancel. But they were going to demonstrate this, and so on, and well, that's that. So I believe now physicists have found some way of doing the other side of the thing, but it doesn't really affect us here at all. So this is the most important thing, that Newton, as far as Goethe is concerned, starts with a finished product and reads it back into the origin, whereas he follows through the coming into being. Now, one more step, and then I can stop talking, I guess. One more step, and that is, I want to now, oh yes, two more steps. Aren't you unlucky? Two more steps. I don't want to go too much into this, but it's important. Newton claimed to have done this purely by experiment. He called it reasoning according to the experiment. It was really his attempt to do a Baconian thing. Newton was a gigantic genius. He was the greatest mathematical physicist there's ever been, right at the beginning. What he did in the mathematical principles of natural philosophy with the science of motion and gravitation is beyond belief. And yet at the same time, he also was on the empirical side. And here he's doing an empirical experiment in what he believes is the Baconian manner. He's the only person I know who combined these two. And when he took over the Royal Society and ran that, he had people doing new experiments, weekly meetings every week. Well, obviously weekly meetings would be every week, wouldn't they? But you know. And this is really the Baconian side of Newton. But there is more to it than that, because people said at the time, you know, the reason why you're thinking this, Newton, is because you've got a mathematical model here. No, I haven't, he said. But he had. We know that because it's in his notebooks. And this was the corpuscular model, because the mechanical philosophy, which Newton extended by introducing non-mechanical forces, much to the annoyance of the French, the mechanical philosophy was a corpuscularian one, which said that everything is made, coming through from Epicurus, the Stoics and so on, everything is made, ultimately, of tiny corpuscles, atoms in motion. Some people thought they were atoms, you couldn't divide further. Some people thought they were corpuscles, you could always divide into smaller corpuscles. It doesn't matter. And so the idea was to try to explain everything, ultimately, in terms of corpuscles in motion. And this is what Descartes' huge project was. And really said that in the back of his mind, Newton had that was a mathematical physics, because you need to do the mathematics of that. That he had in mind the idea, thank God they're not coming in, I'll never get back to this really. Had the idea that light really consisted of a stream of corpuscles. And so what happens to it, you go and work for a mechanical explanation. So you can do it any way you want. You can say, for example, let's supposing some corpuscles are travelling faster and some slower. So let's have, if we have, for example, if the red are travelling faster than the blue, the red won't spend so much time going through the prism as the blue. So they won't be affected by it so much. So red will be refracted less than blue. Hey, it's an explanation. And then you can add some mathematics to it. I was actually taught that one at school. Oh, but it might be serious. You might say, well, yeah, but you could do this. How about size? Yeah, let's do size. Let's say the red corpuscles are bigger than the blue corpuscles. So the red corpuscles don't get bent so much round as the blue corpuscles. Oh, that'll do it. And then you can easily put some mathematics to that and come up with an explanation. And I said, you see, this is what Newton had also in the back of his mind. And he denied it, but it's there in his notebooks. Of course, there's a problem here, because in the philosophy of atomism, the corpuscularian philosophy, there, of course, as Galileo and others have pointed out, this means that there's no colour in the world. The colour is only in human experience. These corpuscles, we talk about red, blue. It's really red-producing corpuscles, blue-producing corpuscles. They're not red and blue. There's no red and blue in the world. Everything's colourless. These colours only occur in human beings when they enter into our eyes and affect the nervous system, according to this approach. So although people talk about red and blue, etc., that's just a way of talking. They've actually got no colours at all there, so that makes it even more complicated. It gets very muddled up. But now what I want to do is just mention the final thing, almost, and that is to go to what Newton says in his later book, in the Optics of 1604. Because if you look at the part there on colour, he starts it in a completely different way. Anything he says in this paper of 1672. He says, if you take a thread, a piece of cotton, piece of wool, I don't know, a thread, and you make one half of it blue and the other half red, and you hold it up against a dark background, and then with your third hand You take a prism, and you look through it. You will see that the blue is depressed down below the red, thus showing that blue is refracted more than the red by that prism. That's the basic observation, and he starts from there. And this he does in 1604. Now, in fact, that observation is there in a notebook in 1666, 1667, 1668, I can't remember which. Rupert Hall was the man who wrote that book. Rupert Hall. And I found this in a paper by Rupert Hall, by accident, when I was teaching physics. And quite by accident, that this observation, where he begins his colour work in 1604, was there already before he'd done the first paper. And so it was immediately clear in my mind, in that moment, I saw the idea. Newton had the idea of differential refraction all along, long before he actually did this experiment where he said he discovered it. And I can't believe for a moment that that didn't influence him. So I think this is the crucial thing. And he doesn't give the game away to begin with, because he's doing it all out there. Later he does, he says you look through a prism at this coloured thread, and the blue is depressed more than the red. That's differential refraction. And that was, I'm sure that was in his mind when he did his first experiments. So he already had the idea of differential refraction before he did the experiment from which he said he discovered differential refraction. I just feel sure that we can now see how Goethe would deal with this observation, because at huge expense I have arranged some coloured cards. Now I think there are only 10 that you can share, and this is fun. Well, there's more than 10, but there's only 10 one kind. Here we go. This is, yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Therefore, since you're sitting there on your own, you can have one. It's too awkward for people in front of the light to share. You could share. One. Two people have disappeared here.
Just one.
This one. Here we are. One for you. You two could share. And then where are we? Here we go. Philip doesn't get one. But Philip does get one. Because I could give him the posh one.
I can share also.
Can you share?
Yeah.
So I'll have to go and buy the posh one.
I'll try that.
Well, I'll have to guess. No, I know it. I just have to visualise it. Just hope I get it right. If you look at the bottom one or top one, the blue and red one against the dark background, that's what Newton is describing with this thread. Now, what do you see?
Yeah, Louis stays down.
Is it shifted?
Yeah. Louis stays
Would you like to look a bit more closely? Which one's shifted?
Oh.
Red.
The red.
Well, yeah, because I can only see the
Has
spectrum.
the red gone up or has the blue gone down?
Red's gone up.
Well, Newton says the blue's gone down, but it doesn't really matter. But what is actually happening? Look very carefully.
There is no yellow in the red.
Look at it.
It's
They're both lighter. They're both those oblongs, the red one and the blue one, are actually lighter than the dark. That's important. If they're lighter than the dark, then what we're looking at Here we are. What we're looking at is that, with each one of them. One's red, one's blue. They're lighter than the dark. So this is the situation. So what colours have you got at the top? On both of them, you've got red, orange, yellow. What colours have you got at the bottom? You've got the blues. Now, if you look at the way in which those edge colours combine with the black background, in one case you can't see them. And therefore they seem to be cancelled out. The result of which it looks that the blue has been pushed down. I'm pushing you into this now. The blue has been pushed down. Can you see that?
Yeah.
And that's because you're not seeing the edge colours at the top. But they're there. And you can get to see them. And therefore there is no differential refraction. And this is what Newton observed. And he didn't take into account the background, the context. He only looked selectively at the thread. And he saw the situation is there is a thread. No, it's not. The situation is there is a thread against a black background. This is selective thinking. If you select that bit out, it looks like differential refraction. See it against the background, and you see, no, there's no differential refraction. So Newton's observation, with which he starts to part the colour in 1604, is wrong. And it's wrong in his notebook in 1666, 1667, or whatever it is. So that I believe is the observation which he didn't let on about in 1672, had already given him the idea of differential refraction, and then he purported to discover that from this experiment. But he'd already put it in the experiment in the first place, I believe. This is my take on Newton, which I have written up in my book, page 200 and something or other. There's quite a lot in there on this. And there you are. So that's very fascinating to me when I realised that, again, one of those, there's a word for it, isn't there? Serendipity, what's the word? Well, there'll be a word, there's always a word. Serendipity. I was bored. I had a whole day teaching, and I enjoyed what I was doing. I love teaching physics. By the end of it, so much has gone out of you, you feel flat. And you feel this boredom. He knows it, he's shaking, he's nodding his head. And you feel this boredom. And I wandered through into one of the other labs, the head of physics lab. I was leaning on his desk, big bench, and he got this science teacher's review there. And so in a desultory fashion, just flicked through the pages, feeling bored. The name Rupert Hall, I then remembered Rupert Hall was. I looked at that, started to read it, bang, I wasn't bored then. I suddenly realised what I was looking at. He said, this is there in his notebooks before the rest. So that was how I discovered it, entirely accidental. This is the value of boredom is immense, actually. Heidegger gave a whole term's course on boredom, which is very interesting, really. Anyway, of course, then you can go further, but I don't want to. You can. What Goethe then does is he not only looks at the context. I must mention this. So he sees comprehensively instead of selectively, but he then puts things back into their context. He then, does it synoptically. That is, he works out, he calls it manifolding the phenomenon, producing the differences of the phenomenon. And he says, you manifold the phenomenon. So he will then do the same experiment, but he'll put it on a white background. And then what will he do? He then decides, well, he'll put all the colours together on a black background and on a white background. And then he thinks, well, why not go the whole hog? Let's have everything together, all the colours on a white background and a black background all together, and then you look at that. And so this gives a complete, what later gets called a synoptic presentation. And this is what Wittgenstein was so taken with, this idea of a synoptic presentation. Bring all the different uses of a certain language used together, all the different ways this is done, and make a synoptic presentation. Then you will understand, and then you get the fact. So this is what he did. And that, we're not going to go through and do this, but you can play with it if you want to in a minute. Because I'm just going to finish off here. Because what I really just want to say to finish off, well, I've more or less said everything, but this is what I would call Goethe's phenomenology of colour. And I mean that not in the physicist sense, but in the phenomenological sense. He's actually working phenomenologically, seeing the idea in the phenomenon. And that's a different way of working. But Newton wasn't working phenomenologically. He was bringing the idea to the phenomenon. It was quite a different kind of thing. And Goethe did talk about this. He said, his method, let the facts themselves speak for their theory. In other words, the facts will speak for their theory. They will say their theory to you, speak. Let them speak for their theory. In other words, the theory will appear in the facts. This is phenomenon-centered science. What mainstream science is theory-centered science. It says we begin from the phenomenon, but what mainstream science does is it actually puts a theory in the centre as soon as it can. So it's theory-centered science, whereas this is phenomenon-centered science. So let the facts themselves speak for their theory. Now then, he says, don't look for anything behind the phenomena. They themselves are the theory. And people have tried to interpret that all sorts of ways. But phenomenologically, don't look behind the phenomena. They themselves are the theory. The theory appears in the phenomenon. The theory is just the idea here. It appears in the phenomenon. And of course, this takes us right back to what we did earlier in the week about the appearing, and the appearing of what appears and so on and that. As Heidegger put it, the phenomenon is that which shows itself in itself. That which shows itself in itself, which of course is the same as Husserl's. The phenomenon is what appears as appearing. And that's what you have here, this appearing. The theory appears in the phenomenon because it is the phenomenon. It's as if there's a depth in the phenomenon, but the depth is intensive. There's not something behind the phenomenon. Oh, there are corpuscles behind it. No. You go only into the phenomenon, and then the idea appears in the phenomenon, shines forth from the phenomenon, appears, and you see. And the thing is, that's very important, is that seeing, when you see the idea appears. Because seeing the idea is the appearing of the idea. We think of them separately. We think of seeing and appearing, or appearing and seeing. Seeing, it's not that there's two either. Seeing is appearing. What we call seeing, in this case, when something new happens, like Duchenne and muscular dystrophy, in this case, seeing is appearing. And you can't have something appear without being seen. You can't say, oh, when did it appear? Oh, it appeared 5 minutes ago, but nobody's seen it yet. It doesn't make sense, you know. So appearing is seeing. And in discovery, seeing is appearing. There's two ways of talking about the same event. And that's, here you see, this is phenomenology. Now seeing is appearing. Appearing is seeing. We're right up at that. We're now upstream in the phenomenology again. And we find this with the quite simple recognition of ideas in science when it's done phenomenologically. It's quite astonishing. So what we've actually been doing here, in its own way, is an illustration of what I was talking about earlier in the week. But we wouldn't normally think of it that way. And then he says, the greatest achievement would be to understand that everything factual is already its own theory. And he does say it would be a great achievement. In other words, we haven't got it yet. You're not going to start with that. That's got to be achieved. The greatest achievement to understand that everything factual is already its own theory. But it has to appear that way. And then the fine Cassirer, Ernest Cassirer, was a philosopher at the beginning of the 20th century, who has been somewhat eclipsed in recent years because he was sort of done down by Heidegger in a very famous meeting around about Davos in about 1930. Then he had to leave because of the Nazis, and he went to America, where he made a big impact, but then he died and wrote a lot of stuff. But the thing is, it's very interesting. The signs are the books are beginning to be published on Cassirer again. This happens. Philosophers come back. And he was steeped in Kant and Goethe. And he said that with Goethe, he said, the mathematical formula strives to make the phenomenon calculable. And that's, of course, what you do in optics, because optics is really technical optics. You're not interested in the nature of light. You're not interested in the nature of colour. You want equations which you can do calculations with to arrange, organise and sort out optical instruments. So the mathematical formula strives to make the phenomenon visible. That of Goethe, I got that wrong, strives to make the phenomenon calculable. That of Goethe, that is Goethe's formula, strives to make the phenomenon visible. And I think that's very interesting because we would actually say, well, that's very strange, isn't it? Surely the phenomenon is what is already visible. But now we've seen that, no, it's not. It's only begun to be visible. It's like an iceberg. There's a bit above the surface, but there's the rest, which can be made visible by working in this way. And that's what Goethe does. He strives to make the phenomenon visible. What does that mean? It means the phenomenon appears. So we're back to appearing. And the appearing is the seeing which sees it. That's the astonishing thing. There's no separation there. The appearing is the seeing that sees it. There's no subject-object separation or anything like that, because we're right upstream. And that means that's where the phenomenology brings us. And so we come into a completely dynamic way of understanding. And at that point, I'm going to shut up.
Spelling earlier that turned out to be a little bit revealing. When you were talking about the universal and the particular, at one point you quoted, I think, the case of the particular bearing the universal.
Oh, did I?
And no, it's a good quote there. So I wrote it down, B-A-R-I-N-G.
Oh, yes.
Megan wrote it down, B-E-A-R-I-N-G, which I think is the way it was meant.
Yes.
And Adriana said, how do you spell that? So of course I told him my spelling. Megan said, no, it's the other way around. But we realized that in fact there are two complementary ways of understanding the phrase.
Yes.
Bearing is just to bear itself, reveal itself.
Yes.
And bearing in the sense of carrying. And
yes. I must say it's very interesting. Yes. That I can see that both ways. Yes, I can see that. Thank you.
In order for what you just said in the final stages, which is really exciting, is the phenomenon of becoming visible and its appearing, there needs to be an observer. An observer then would be absolutely relational to that appearing, and it cannot occur without the observer.
No. That's right, and that's what we came towards on Tuesday. And this is one of the great questions that comes up in phenomenology. It's what they call objectivity for subjectivity, hyphenated. That doesn't mean it's a fake kind of objectivity. What it means is things only appear in seeing. Therefore, there must be seeing. Therefore, in that sense, there must be an observer. It's a question of whether one's understanding that in a downstream sense, if there's the phenomenon all there, like an object, and here's an observer over here separate from it, and a subject, and the subject's going to observe the object. If you start downstream there, you've had it. You run into all the epistemological problems. But you see, phenomenologically, at the point of discovery, the point of appearing, that is seeing. And there couldn't... It goes back to, we are the appearing. And that is the phenomenon. And so, in that sense, the phenomenon, as it were, in one way the German idealists used to say, Schelling and so on, that in fact the phenomenon reaches the highest level of itself in human being. But I don't like that way of putting it. I used to try that, but I don't think it worked. I shouldn't have mentioned it. I think in phenomenology you can do it much more directly. It is the appearing. And it goes further. You wouldn't have thought it could go any further than that, but it has done. The more recent developments about the whole notion of givenness. That what appears, there's a certain quality of givenness, not a giver, but given. And the phenomenology has now taken that direction. You wouldn't have thought they could have gone any further than this, but they have done. And Jean-Luc Marian has done some remarkable work on the phenomenology of the given, which I haven't understood, worked with. I hope to do something on that this winter.
What is his name?
Jean-Luc Marian. But it's not easy. It's not easy.
Wouldn't it be more useful, or could it be more useful to use the term or think that in terms of participant rather than observer?
Yes, you can do that. A lot of people do. And you may have wondered why I haven't done it. Well, because I noticed that when people start talking about being participant, they get it the wrong way round. We are the ones who are participated. We talk about ourselves participating in something, but we are actually being participated. And it's the other way around. And the way we talk about it, participation turns into another form of egotism. Wow, I'm participating in God. Fantastic, eh? The other way around, it actually leads to something quite different, which is more a kind of, I don't know what you call it. But you realise you are the one who is being participated, then you have a responsibility to be able to be participated. And that's quite something. So participation's fine, but you've got to get it the right way round. There's a bit where I did do this with the hermeneutics. I can't remember what it is. Because this is there in Aristotle and things. In this case, if you would, you can do it in Aristotle's way, in which case you would then say that we are becomed by the phenomenon. You say we are becomed by it. I can't remember. I've got it. I've got this. I can't remember the words I used. Something like that. And then you get away from all these problems, and that's real participation. A lot of the stuff that's participatory is fake. Did you find that yourself?
Yeah.
So that beautifully illustrates the difference between the counterfeit and...
Yes, it does. Yeah. Yes, it does, yeah. So I tend not to use the word participation because I know it goes that way, but it is genuinely participative. And I mean, we're in the exploration of this. In the 20th century, this is what's been happening in European philosophy, often not noticed, but it's a movement that's going on, and perhaps in 200 or 300 years' time, if we're still here, this will be much more filtered into things much more, this way of thinking. As things from the past, when we now think in ways which were very new in the 17th century. To us it's now common sense. Most unfortunately, that common sense happens to be wrong. But, limited. But on the other hand, it also produced things. So not quite right to say it's wrong.
would you then say if a new form appears in nature, that it's been seen?
I haven't quite followed you.
So this thing, it's not just if a new form appears in nature, so that self-differencing has found a new way of expressing itself.
Yes.
Then can you say that in some sense it's been seen?
I don't know the answer to that question. This is a problem. They used to, of course, get around it by saying, well, God's there, God sees it. But you can't do that now. So I don't really know how to... Forms will appear, but they don't appear. It's very hard, because, see, I've got the problem. I can say forms will come into being, but actually I'm also using the notion of being in terms of appearing. So it's a problem. I've got that problem. And I don't know how to resolve that problem. But obviously nature develops, and nature developed without human being. So I don't know what you can say, but there's obviously nature is there. I mean, we could cease to exist and things would be there. Planets wouldn't disappear if we disappeared. And planets were there before we were. And so that's it. But they're not there appearingly. But we imagine them as being there appearingly. And that's right. The thing is, when things appear, the fact of appearance is actually really quite miraculous. And that's something that happens with human beings. Now, it must also happen in some ways with horses or whatever, but can't be in the same way as it is with us. And I think this is something which is not clear.
Wouldn't that not be about everything, bringing everything else into being? Whether it's, if you think of everything as having sentience, if you do, then could that, taking human beings out of being so central in the picture, could it not be that everything that's sentient or some kind of a life form is kind of evoking each other all the time?
Well, it could be, yes. Yes, it could be, and there are people who want to think in that way, and maybe there's some way of going in that direction. It certainly seems to me, yes. But I still do think that actually in the appearance that happens in human being, there's something quite specific happens. But I certainly think that way of looking at it has a great deal of potential for exploration of it, because that would actually certainly be very good in terms of taking a different attitude towards nature. I think that's important, what you've just said, to follow that up. And it's a doorway through which this could become more universalized. But it wouldn't be done in the same way as in human being. But we did mention this the other day, didn't we?
Could a way of inquiring about that be through a relational context?
Yes, a relational context, yes. Is that the gong?
Yeah.
That's it then. I'm knocked out. I'll go home now. I'm getting embarrassed now.